A nuclear reactor is a type of furnace in which energy is generated by a controlled fission chain reaction. The first nuclear reactor was built by Enrico Fermi in 1942 on the floor of a squash court under the west stands of Stagg Field at the University of Chicago. Today, there are many different kinds and sizes of reactors, and many have the same three basic components: fuel elements, a neutron moderator, and control rods. The fuel elements contain the fissile fuel and, for example, may be thin rods of about 1 centimeter in diameter. In a large power reactor, there may be thousands of fuel elements placed close together, and the entire region of fuel elements is known as the reactor core. Uranium-235 is a common reactor fuel. Since the natural abundance of this isotope is only about 0.7%, there are special uranium enrichment plants to increase the percentage. Most commercial reactors use uranium in which the amount of uranium-235 has been enriched to about 3%. Whereas neutrons with energies of about 0.04 eV or less readily fission uranium-235, the neutrons released during the fission process have significantly greater energies of several million eV or so. Consequently, a nuclear reactor must contain some type of material that will decrease or moderate the speed of such energetic neutrons so that they can readily fission additional uranium-235 nuclei. The material that slows down the neutrons is called a moderator. One commonly used moderator is water. When an energetic neutron leaves a fuel element, the neutron enters the surrounding water and collides with water molecules. With each collision, the neutron loses an appreciable fraction of its energy and slows down. Once slowed down to thermal energy by a moderator, a process that takes less than 10 to the negative 3 seconds, the neutron is capable of initiating a fission event upon re-entering a fuel element. The released energy is used to heat pressurized water that is cycled through the other mechanisms of the plant. If the output power from a reactor is to remain constant, only one neutron from each fission event must trigger a new fission, as seen here. When each fission leads to one additional fission, no more, no less, the reactor is said to be critical. A reactor normally operates in a critical condition because then it produces a steady output of energy. The reactor is subcritical when, on average, the neutrons from each fission trigger less than one subsequent fission. In a subcritical reactor, the chain reaction is not self-sustaining and eventually dies out. When the neutrons from each fission event trigger more than one additional fission, the reactor is supercritical. During a supercritical condition, the energy released by a reactor increases. If left unchecked, the increasing energy can lead to a partial or total meltdown of the reactor core, with the possible release of radioactive material into the environment. Clearly, a control mechanism is needed to keep the reactor in its normal or critical state. This control is accomplished by a number of control rods that can be moved into and out of the reactor core, as shown here. The control rods contain an element, such as boron or cadmium, that readily absorbs neutrons without fissioning. If the reactor becomes supercritical, and the power output increases at too high a rate, the control rods are automatically moved into the core to absorb the excess neutrons causing the condition. In response, the reactor returns to its critical state. Conversely, if the reactor becomes subcritical, the control rods are partially withdrawn from the core. Fewer neutrons are absorbed, more neutrons are available for fission, and the reactor again returns to its critical state. Here we show a pressurized water reactor. In such a reactor, the heat generated within the fuel rods is carried away by water that surrounds the rods. To remove as much heat as possible, the water temperature is allowed to rise to a value of about 300 degrees Celsius. To prevent boiling, which occurs at 100 degrees Celsius at 1 atmosphere of pressure, the water is pressurized in excess of 150 atmospheres. The hot water is pumped through a heat exchanger, where heat is transferred to water flowing in a second closed system. The heat transferred to the second system produces steam that drives a turbine. The turbine is coupled to an electric generator, whose output electric power is delivered to consumers via high-voltage transmission lines. After exiting the turbine, the cooler steam is condensed back into water that is returned to the heat exchanger via a pump.